All right, here's page 2. You have a forklift that pushes a 100 kilogram crate starting from rest, force magnitude F. The graph shows the x component of this force as a function of time. What is the instantaneous velocity of the crate at time t equals 10 seconds? So if it started from rest and you go out to 10 seconds, this graph, the area, which is F times t, we're actually integrating this, will give us our impulse, but we know that's also equal to delta p. So really this area is going to represent m delta v. So if we, well, m we know, it's 100 kilograms. We got to find this area first, and then we'll divide by m to get what delta v is. So j divided by m. So the area divided by the mass will tell us what delta v is. If I break this into two parts, see them there. This first area is just the area of a rectangle. It's 5 times 10, so it's negative 50. Newton seconds is the unit, if you wanted to know. And this other area here is 1/2 base times height, which is negative 25. So your total area is negative 75 Newton seconds or kilogram meters per second. They're the same units. Divided by the area, divided by the mass, which is 100 kilograms, and you get negative 0.75 meters per second. And that's your delta V, but it started from rest. So basically your V final equals negative 0.75 meters per second. The answers are in centimeters, so I'm going to change this to negative 75 centimeters per second. The answer to this one, I believe, is D. Tiger's running in a straight line. If we double both the mass and the speed of the tiger, so what if question? What if? What happens to the magnitude of the momentum? So P is equal to mv. If we double the mass and double the speed, we have 4 mv. This was our original, so our new one is 4 times as much. Pretty simple. Block of mass m equals 3.6 kilograms. Frictionless surface with a V initial of that makes it suddenly perfectly elastic collision. That's helpful because it gives us that extra set of equations. It collides with another block of mass capital M. You can see it in the picture. Just after the collision, the 3.6 kilogram block recoils with a speed of 2.7. What is recoils is important because that's the opposite direction. You better think negative sign. What is speed v of the other block? So if I do p before equals p after, I can say m v initial plus big M v big M equals m v little m prime plus big M v big M prime. This one was at rest. It was a stationary block. So I have 3.6, I'm going to leave out units, times 9.3. I'm going to say 9.3 is positive. We'll say it's to the right based on the picture. Equals 3.6 times, now this V prime is this 2.7 number, but it's negative because it says a recoil, plus big M times V. Now look at this, we have no way of knowing what either of these two are because we only have one equation. But because it's a perfectly elastic collision, we can also say, and I think we've written it a bunch of different ways, but I'm going to write it this way this time. VA plus VA prime equals VB plus VB prime. This might be the easiest way to remember it. The other way has subtractions and negative signs, but when you work it out, this is what it looks like. So 3.6 6 minus 2.7 equals 0 plus VB prime. So I think we're already done here. VB prime, which is V of the big mass, equals 0.9 meters per second. And I just checked my key and realized I made a mistake. This is not 3.6, it's 9.3. That was the mass. So 9.3 minus 2.7 is 6.6 meters per second. Yeah, 0.9 was not an answer here, so I don't think that's going to work. So there's your answer. You didn't even have to do this initial stuff. Waste of time. Sorry. In a certain nuclear reactor, neutrons suddenly collide with deuterons, which have twice the mass of neutrons. In a head-on elastic collision with stationary deuteron, what fraction of the initial kinetic energy of a neutron is transferred to the deuteron? I'm going to pause and erase because this is going to take a lot of space. Alright, this one's fun. So in this collision, P before equals P after. So we have mass of the neutron, V of the neutron, plus mass of the deuteron, V of the deuteron. It's head-on elastic collision. So head-on elastic collision, we have our special formula where it's VA plus VA prime equals VB plus VB prime. We're going to need that. The deuteron is stationary, so initially, or before, I can make that 0. Let's finish what this is going to look like. Mass of the neutron, V of the neutron prime, plus mass of the deuteron, V of the deuteron prime. Now they tell us the deuterons have twice the mass of neutrons, so we can rearrange this a little bit or replace this and say Mn Vn prime plus the mass of the deuteron is 2 mass of the neutron times V of the deuteron. And when you do that, the MNs drop out, which is good. So you have V, the neutron before, equals V of the neutron after, plus 2V, the deuteron after. Now where are we going? What fraction of the initial kinetic energy of the neutron is transferred to the deuteron? So we have to look at kinetic energy, and we can obviously use this equation if we want. So let's write that. V of the neutron, so this was 1 from momentum. This is 2 from our kinetic energy elastic collision conservation formula. So Vn plus Vn prime equals V deuteron plus V deuteron prime. We already said before this was 0. So we get Vn plus Vn prime equals Vd prime. If we solve for Vn prime, we get Vd prime minus Vn. And the reason why we want to do that is we want to substitute, where is it, this one into this one. And we're going to get Vn and V deuteron, and we'll look at what the fraction is after that. So Vn equals, I'm going to take this and substitute it in here, Vd prime minus Vn prime plus 2Vd prime. If I bring it to the other side, oh shoot, that's not a prime right there. Plus Vn, and I get 2Vn equals 3Vd prime. At this point, you're probably wondering, why am I doing all this? We want to look at what the fraction is of the initial kinetic energy of the neutron is compared to the kinetic energy of the deuteron. Actually, I don't know if that's how I want to look at it. what fraction of the initial kinetic energy of a neutron is transferred to the deuteron? So I think I want to flip this. You're talking about transferred to this. So KED over KEN. And what you're going to see is 1/2. The mass of the deuteron is 2 times the mass of the neutron. And the V of the deuteron, I should probably solve for it, equals 2/3 of Vn. And I hope you're starting to see the idea of this is every term is going to cancel out except for a fraction. 1/2 mass of the neutron, and this is just Vn squared. So the 1/2s go, the MNs go, the Vn squareds are going to go, and you're left with 2 times 4/9, which is 8/9. And that is your answer for how much kinetic energy is transferred to the deuteron. I hope this question's a little easier. Identical forces act for the same length of time on 2 different objects. So same force, same time. So J is the same. The delta P is also the same. But if they're different masses, obviously delta V will be different. So let's see what it says. The magnitude of the change in the momentum, so this is a trick question, the change in momentum is going to be the same of the lighter object is exactly equal to the change in momentum of the larger mass. It's just a trick question. If they asked for what was the change in velocity, then you'd have a difference.